I'd like to do a slightly more complicated example of an electrode potential type problem. And what we're looking for here is E naught cell, delta G naught, and K, and we're saying this is a standard cell. Standard cell means that all the solutions are 1 molar, all the pressures are 1 atmosphere, and that's what we're going to be saying. If we pretty much assume that's what it is, unless it says otherwise. We'll look at some non-standard cells in a little bit, but looking back at this one, we've got copper 2 plus and copper. This is on the left side. And in these cell diagrams, the anode's always listed first. And it's a good way to remember that. We say anode is before cathode, A comes before C in the alphabet. And we know that oxidation occurs at the anode. So we know that any reaction we find on the reduction potential table that involves these two things will need to be flipped. And that's what I'm going to do. So I'm going to hunt down the reaction that involves copper 2 plus and copper. I'm going to, of course, find that on my reduction potential table. And let's see if we can find it. We've got copper 2 plus and 2 electrons. There we go. Copper 2 plus, 2 electrons, and copper. That's the one we want. Positive 0.340 volts. This is for the reduction. We need to change this into an oxidation process. So what we do is we take the reaction we see on the reduction potential table and we simply flip it. And that's what I've done. Put the copper solid on this side, put this other stuff on this side. In so doing, I flip the sign from plus 0.340 to minus 0.340. Remember, I had to do this because this is the anode and oxidation occurs at the anode. These are reductions. I needed to change it, so I had an oxidation listed for this particular reaction. Next, I have to hunt down something that involves H2SO3, H2SO3, H3O+, and sulfur solid. Ooh, where are we going to find that? There we go, H2SO3, H+, and sulfur. Now you might be saying, well, hang on, this is H3O+, that's H+, but if you look back to test 2, you'll realize that H3O+ and H+ are one in the same. These are all aqueous solutions. If it's H+ in water, this is what it is, it's H3O+. So if you see H3O+, don't worry about it, just think of it as being H+ and you'll be okay. So I just copy this reaction down as it is, exactly over down to here. Now the thing is, this is a reduction, and since these are reductions, I don't change this reaction at all at this point. Alright, we still need to balance this process. We've got 2 electrons up here and 4 electrons down here. We need to balance this so we can get rid of the electrons when we add the reactions together. Now the way I can do that is to multiply this top reaction by 2. And so that's what I've done. That'll give me 4 electrons here to match the 4 electrons here. When I add these together, the 4 electrons will cancel. Alright, so I go ahead and do that. The 4 electrons are gone, and I've got my final reaction. Now keep in mind, when I multiplied this by 2, I didn't touch the E naught. The E naught value stays the same. And if you go back to the previous mini lecture, you'll see my reasoning for that has to do with this being this voltage being an intrinsic property. Doesn't matter what I multiply this by, it ain't going to change the voltage. It'll still be minus 0.340 volts. So I add the reactions together, I add the E naughts together, I get my E naught cell value. It's positive 0.109 volts. So this would be a spontaneous process, I know that, because the E naught cell is positive. I can go ahead and calculate the delta G value. The delta G naught value will be the negative n, which is number of electrons transferred in the balanced equation. We go back to the original equation. Here we go. 4 electrons transferred in the balanced equation. So that's going to be my n value. F 96485 joules per mole, that's Faraday's constant. There's our E naught cell, and I convert it to kilojoules, minus 42.1 kilojoules per mole. The last thing I can do then is to get my K, and I do that in the same way as I did when we did the thermodynamics problems earlier on. So we just substitute in our value for delta G, making sure that we have it cancel with the value of R. With the units, that's going to be joules, that's kilojoules, so I convert this to joules as well, and this will give me my value of K as 2.40 times 10 to the 7th. If you need more information about this, go back to the mini lecture where we talk about the calculation of K from delta G naught.